When we move into 8.2, we are talking about graphing polar forms and working with vectors. If you've done much physics, you have probably talked about vectors. We usually leave the in-depth discussions of vectors to our physics and science instructors, but a vector is just a direction. It's a distance with direction. So it's like a directed line segment. If you're going to shift something according to a vector, like for example, this vector 2 minus 3i would be to the right 2 and down 3 if I didn't have that I there. When I'm talking about using vectors in imaginary numbers though, I need to talk about graphing on, I'm moving toward graphing on a polar axis. To graph a complex number such as 2 minus 3i, we are modifying the familiar coordinate system by calling our horizontal axis the real axis and the vertical axis the imaginary axis. Then my complex numbers can be graphed in this complex plane, because instead of just our real plane with x and y as horizontal and vertical, now we have just basically renamed it so that it's the complex plane. So we have an imaginary axis and a real axis. Each complex number, a plus bi, determines a unique position vector with its initial point at the origin, 0, 0, and the terminal point at some value a, b, where a is my real coefficient, the real part to my complex number, and b is the imaginary part to the complex number. So you still move the directions you think you're going to move, but our x-axis represents the real part and the y-axis represents the imaginary part. Notice that when I graph, I don't just have a segment or a dot, I have a vector, a directed line segment with an arrow at the end. The stopping place is that 2 minus 3i. This geometric representation is the reason that a plus bi is called the rectangular form of a complex number. Rectangular form is also called the standard form. So we are going to be talking about in the next section the polar form, but right now we are going to concentrate on this rectangular form. Then we're going to introduce the polar form and be able to work back and forth between the two. The sum of complex numbers is called their resultant. So when I add two complex numbers together, the sum is the resultant. It says to graph both of these numbers and their resultant, or their sum. So let's find the sum first, and then we'll start putting things on the graph. So if I take 2 plus 3i and I add to it negative 4 plus 2i, I get negative 2 plus 5i as the sum or the resultant. Okay? Let's graph first our two complex numbers. 2 plus 3i is going to go to the right 2 and up 3. So we go to the right 2 and up 3, and that gives us the stopping point of that vector. The vector is this directed line segment, ends in an arrow. Then I have negative 4 plus 2i. I go to the left 4 and up 2. That's the stopping point of that directed line segment, or that vector. Ends in an arrow. And then the resultant is always going to fall between them. The resultant is the sum. The sum in this case, or the resultant, is negative 2 plus 5i. So I go to the left 2 and up 5, and that's where that vector or directed line segment ends. And if you look, you see kind of this is a rectangular form. You see it's not specifically a rectangle usually, but it's some type of parallelogram that they form, where that resultant is between the two complex numbers that you got it from. We have another example on the next page. Go ahead and find the resultant and graph both the complex numbers and the resultant. In this case, the resultant, or the sum, is 2 minus 5i, and it falls between our two complex numbers. 6 minus 2i is that first vector. Negative 4 minus 3i is where that second vector ends, and their resultant, or sum, was 2 minus 5i. And notice that they all start from the origin. You don't have to draw the little dots in between to show that parallelogram. They all start from the origin. That's their initial point, and then that location is their terminal point. That's the rectangular form, or the standard form. Now let's look at the polar form of our vectors. We have relationships among x, y, r, and theta. So you know these relationships. First of all, we've got cosine theta is x over r, and sine theta is y over r. So if I solve for x here, I get x is equal to r times cosine theta, correct? Another way to think of this is using our Pythagorean theorem. You know that r is the square root of x squared plus y squared. What about sine theta? Well, if I solve sine theta for y, I get r sine theta. Another sine, cosine, and tangent. Tangent is y over x, as long as x is not 0. So we are going to use this information to find our x and y coordinates, r cosine theta and r sine theta. This r value, square root of x squared plus y squared, is what we're going to call the modulus. The modulus is our absolute value of x plus yi, our complex rectangular form. And then we're going to use this formula for tangent, this equation for tangent, because it allows us to find theta. It allows us to find theta. Okay, trig, or polar form of a complex number. We've talked about the rectangular, or the standard form. Now we're going to talk about the trig, or the polar form of a complex number. This is it right here. R times cosine theta plus I sine theta is our trigonometric, or trig form, also called the polar form of our complex number, x plus yi. That's the rectangular form. This is the trig form, or the polar form. This expression, cosine theta plus I sine theta, you've got c theta plus I s theta, is sometimes abbreviated as CIS theta. So cosine theta plus I sine theta can be abbreviated this, CIS theta. Using this notation, r cosine theta plus I sine theta is written as r CIS theta. So you can either write it out the long way, or you can shorten it and use the abbreviation. So remember, this is just kind of a new piece to our language. You know the language of math, and we're just adding a little bit of new vocabulary. Instead of looking just at the rectangular form that we're used to of our complex numbers, now we're going to be looking at the polar form of our complex numbers. This doesn't get super difficult. It's really a fun kind of puzzly thing to work through. So we're going to express 10 cosine 135 degrees plus I sine 135 degrees in rectangular form. We've been given our polar form. This is our polar form, or trig form, r CIS theta, where r is 10 and theta is 135. And we want to move to rectangular, or standard form. This way is super simple. You just plug in what you know and distribute. Look at your unit circle. What is the cosine function value at 135 degrees? Well, 135 is one of your 45-degree angles, and it's in quadrant 2, so cosine is negative and sine is positive. And then I have that 10 out front to distribute. When I distribute that 10 inside, I get negative 5 square root 2 plus 5i square root 2, and that's my rectangular form, or standard form, called the same thing. So you do it for r CIS theta, where we have 2 CIS 300 degrees. That's my polar, or trig form. You want to end up in rectangular form. Okay, so where did those values come from? 1/2 and negative square root 3? Those are cosine and sine function values for 300 degrees. Again, you're using your information that you know from the unit circle, or you're pulling out your unit circle and using it to look at. You're plugging in what you know and simplifying to solve for your new trig or polar form. Oh, excuse me, new rectangular form from that trig or polar form. What if I'm given the rectangular form though, and I need to go back into the trig form? Let's talk about going back the other direction. If I'm converting from rectangular to trig form, I need to start by sketching a graph. I want to sketch the graph of x plus yi, my rectangular form. So I'm going rectangular to trig. I want to start with sketching it in the complex plane. Now I want to do that because I want to know what quadrant I'm in. Then, using that sketch, I'm going to find r. Remember our box on the last page. I'm going to find r by using my, I'm sorry, it's the first page of this set of notes. No, it is the last page. I'm looking for it. So when I introduce the trig form, we're going to find r using the Pythagorean Theorem. R is also called our modulus. So we're going to find r using that equation. R equals square root of x squared plus y squared. And then once we found r, we find theta. Because our trig form that we're going for is r cis theta. We have to know r and we have to know theta. We find r after we get our sketch. Then we find theta by using that equation tangent theta equals y over x. That allows us to figure out what theta is since we know what quadrant we're in. Okay, so let's show you how this works. Write each complex number in trig form. So we're in rectangular or standard form. We need to change it so that we're in trig form. I'm going to divide up our area so I make sure I have enough space for every problem. First thing to do is sketch. 8 minus 8i. My real axis is the x-axis. My imaginary axis is the y-axis. So I'm going to move an 8, positive 8 on the real axis, negative 8 on the imaginary axis, and there's my vector right there, where my x-coordinate is 8 and my y-coordinate is negative 8. I need to find r. Well, r is square root of 8 squared plus negative 8 squared. It's the absolute value of the modulus. Absolute value is always positive. Since we're finding the square root but we're not considering plus or minus, it's always going to come out positive. Well, this ends up being 64 plus 64, which is the same thing as 64 times 2. So r is 8 square roots of 2. So we sketched our graph, we found r. The next thing we're going to do is find theta. We find theta using tangent, where tangent is y over x. In this case, I've got negative 8 over 8, which is negative 1. Well, if I'm in quadrant 4 and I have a tangent value of negative 1, what angle theta is that? Well, the tangent function that's negative 1 in quadrant 4 is that 45 reference angle that's in quadrant 4. We're going to answer this one in, it doesn't give us degrees or radians. I'm going to choose for us that we're going to answer in radians. We're going to do some of these in radians, some of these in degrees. In fact, we'll do this left-hand column in radians, and we'll do the right-hand column in degrees, just so that we've worked both ways. The instructions on my math lab will tell you which. But our angle in quadrant 4 that has a tangent function value of negative 1 is that 45, or that pi fourth there. That angle is 7 pi fourths specifically. So we have r and we have theta. Our trig form, remember, is r cis theta, or cosine theta plus I sine theta, and we know what to plug in here now. We know that r is 8 square root 2, and we know that theta is 7 pi fourths. So cosine 7 pi fourths plus I sine 7 pi fourths. And we're done. That is absolutely all we have to do. You see how this is a little lengthy? If I wanted to, I could write it in shorthand as r cis theta. That means the exact same thing. Let's go ahead and do the other one that I said we're going to do in radians before we move over to the right-hand column and do the two that we're going to do in degrees. We're going to use the exact same procedure. We are going to start with a sketch. This time I'm moving to the left and up, so I'm going to be in quadrant 2. I'm going to move to the left, negative square root 3, and I'm going to move up 1 because the coefficient here is a positive 1. So that my vector ends up right there. So x is negative square root 3, y is 1, and I'm looking for r. R is square root of negative square root 3 squared plus 1 squared. Well, negative square root 3 squared is 3, plus 1 is 4, and the square root of 4 is 2. So r is 2. Then to figure out what theta is, because I have to know both r and theta, to figure out theta, I put y over x. In this case, y is 1 and x is negative square root 3, which would be the same thing as negative square root 3 over 3. What is the angle theta in quadrant 2 that has this tangent function value? Well, it's not going to be the 45. It's going to be either the 30 or the 60 reference angle. So I may need to go to my unit circle and play with it a little bit and figure that out. You should come up with theta being 5 pi 6 because that's the angle in quadrant 2 that has this as its tangent function value. So we know all the information we need. Cosine theta plus I sine theta. This is our trig form, our polar form. Now we just plug in what we found. 2 cosine 5 pi 6 plus I sine 5 pi 6. That's my longhand form. Shorthand form would be 2 cis 5 pi 6. Okay, let's move on and do B. For these two, we're going to answer in degrees instead of radians. We're going to start with a sketch. Negative 15. Well, is that real or imaginary? It doesn't have an I attached, so that's the real part, so I'm moving to the left. Negative 15. What about my imaginary part? Well, my imaginary part would be plus 0i, so I'm not moving up or down, so this is my vector right there. So x is negative 15, y is 0. If x is negative 15 and y is 0, what is r? Well, r, we still find it the same way. R, remember we said that modulus, R is the modulus, and it's just the absolute value of x plus yi. Absolute value. X was negative 15, absolute value, that's the positive form, that 15. Now we need to figure out what theta is. Well, hopefully I don't have to even mess with tangent to figure out theta in this case because I can look at it and see that theta is 180 degrees. Remember I told you we can use degrees this time. Theta is 180 degrees because that's where I fell. All right, RCIS theta. RCIS theta is going to be this time 15 CIS 180 degrees, or I could write it out in longhand, 15 times cosine 180 degrees plus I sine 180 degrees. Most of the time it doesn't really matter which one you use. Use whichever one you're most comfortable with. Sometimes it's going to be easier to look at it in this longhand form. You'll kind of start to figure that out as we go through. I mean, you're always able to rewrite it in the other form, so as long as you know what the pieces mean, you're fine. Negative 3i. Let's sketch this one. Well, in this case, my real part, my x is 0, and y is negative 3. So I'm going to go down negative 3 here. My angle then, theta, is 270 degrees. What is r? Well, r is the modulus. 0 squared plus a negative 3 squared gives me an r value of 3. So my RCIS theta is 3 CIS 270 degrees, or 3 times cosine of 270 plus I sine of 270. Either one. Okay, we've got 2 pages of notes left. We're going to do the next page, that example 4 page. I'm going to go ahead and tell you we are not going to do the fractals, the Julia set. Fractals are fun. Fractals are really cool. A fractal is a repeating form where each successive shape is the same shape, but it's smaller. So you can see you've got this big form here, and as we move out, it gets smaller. And then we've got little tails that move off, and they are all the same shape. If you are interested in that and look fractals up, there's a lot of really neat fractals. In fact, I have in my office, I keep a calendar that has fractal patterns on it. However, this is optional, and we're going to opt out of it. We're just going to stop here. Example 4 says that we're going to be converting between trig and rectangular forms using calculator approximations. So our values for theta are not going to be special angles. That's when I know I'm going to need to use calculator approximations. We're going to choose to round to 4 decimal places for our answers here. Make sure in my math lab that you pay attention to what rounding they want you to use. But for our purposes here, we're going to choose to round to 4 decimal places. We are in degrees for all of these. We're going to be using degrees. Again, my math lab instructions should tell you what you're in, but I'm telling you here that all of these, well, for A and C, you know you're in degrees because they give you degrees. For B, you're starting with that rectangular form, so you don't know. It could go either way. We're going to choose to keep everything in degrees on this page. Don't forget that tangent inverse is restricted to quadrants 4 and 1. So I need to think about where, if I'm starting with a rectangular form, I need to think about where that is. Let's do the 2 that give us our trig or our polar form first, which means we're going to be going back to rectangular form for these 2 in the left-hand column. We're starting with the trig form. We're going to be moving them to rectangular form. To do that, we just plug in what we know. Well, I don't know cosine of 205 degrees because it's not on the unit circle, but I can absolutely plug that into my calculator and get cosine of 205 degrees. I don't want to round this until I've already distributed 7 inside. So I'm going to go ahead and write this one down with an intermediate step, but you probably would not write this down with an intermediate step. If you plug cosine of 205 degrees into your calculator, you're going to get a negative value of 0.906307778, and that's where I'm going to round it off, plus I times another negative value, 0.422618. But I'm going to distribute the 7 to each of those. So really what you're going to be doing is doing cosine of 205 degrees times 7. And what you get, rounded to 4 decimal places, is 6.3442, a negative 6.3442. And then minus, because x plus yi, negative 6.3 minus 2.9583i. There's my complex imaginary number in rectangular form. All right, so using your calculator again, you're going to multiply 6 times the cosine of 115 degrees, round it to 4 decimal places. And then multiply 6 times sine of 115 degrees. Don't forget your I, because this is your imaginary part. 115 degrees is in quadrant 2, so cosine is negative and sine is positive. 205 degrees is in quadrant 3, so cosine and sine are both negative. All right, let's look at B and D. With B and D, we are starting with our rectangular form, and we are moving to our trig form. When we're starting with our rectangular form, we have to start with a sketch. Negative 7 plus 2i moves us to the left and up, so we are in quadrant 2. Negative 7 plus 2i, and we need r. Well, r is going to be the square root of negative 7 squared plus 2 squared, which gives me the square root of 53. That's r. And I need to figure out what theta is. Well, theta is not going to be a special angle on my unit circle because tangent is y over x, which gives me a -7/2, and that is not a special angle tangent function value. Notice the angle I'm looking for is in quadrant 2. When I do tangent inverse of this value, I'm going to get a negative angle value because it's going to return an angle down here in quadrant 4. That's where tangent inverse is restricted to. This is negative. When I input it as tangent inverse into my calculator, it's going to give me a negative angle value in quadrant 4 because that's my restriction. My calculator's in degree mode. I'm going to do a tangent inverse of -7 divided by 2. And I get this -74 degrees as my angle. Well, I need an angle that's in quadrant 2. What am I going to do to get it over there? I did the wrong tangent function value, didn't I? Guys, I really need you here with me today. I'm looking at my notes, thank goodness, so I caught myself. What did I do wrong? Hopefully at home you've been yelling at me because I set up cotangent instead of tangent. My y value is 2, not 7. 2 over 7, -2/7. So let's fix that. Let's do tangent inverse of -2 divided by 7. There we go. There's my angle. Still in quadrant 4. Everything else that I've been telling you has been correct. I just set up my tangent function value, the reciprocal form of it. I truly apologize. But it's good for you to see that everybody makes mistakes. I firmly believe that. You need to know that everyone makes mistakes, and when you get a wrong answer in my math lab, you need to go back and you need to figure out what you did to get that wrong answer. Do you not understand the concept, or did you just not pay close enough attention? A lot of the time, hopefully, it's just not paying close enough attention. Okay, so we input a negative tangent function value, got an angle that has a negative value in quadrant 4. But we know that our angle that we're actually interested in is not in quadrant 4, it's in quadrant 2. How do we shift it around there? Well, we add 180 degrees. So the angle in quadrant 2 with that same tangent function value is 164.0546 degrees. Remember, we're rounding to 4 decimal places. So 164.0546 degrees is the angle we're interested in. We started with rectangular form, we need polar form. Polar form is r/cis theta, where r in this case is square root 53, and theta is 164.0546 degrees. I can absolutely write that out in longhand. Cosine 164.0546 plus I sine of 164.0546 degrees. Okay, D. What quadrant will we be in for D? Well, in D, we are actually in quadrant 4. Let's go ahead and sketch that. We're going to go over 5 and down 4, so that's where our vector would end. X is 5, y is -4. R is going to be square root of 5 squared plus -4 squared, which gives me square root of 41 for R. When I check to see what tangent is, let's do it the right way this time. Tangent theta is y over x, so a -4/5. So I'm in quadrant 4. I'm going to get an angle in quadrant 4. Then I just need to figure out, okay, is that the angle that I want to give it as? And I believe my math lab is going to tell you it wants the smallest positive angle value. So when I input this into tangent inverse in my calculator, I get out an angle theta as -38 with a big long decimal. I'm going to go ahead and round it to 4 decimal places, degrees. But if I'm told that I want the smallest possible angle value, I want it to stay here in quadrant 4. Remember, the angles are angles of rotation, so I could rotate a whole rotation and end up here again by adding 360 degrees. That gives me the smallest positive value for theta, where theta is 321.3402 degrees. And when I do r/cis theta, I have square root 41 CIS 321.3402 degrees. Now, we just mentioned angles of rotation. That brings me to what we're going to talk about in the next section. When we're in polar form, can't even spell today. When we're in polar form, there's more than one set of polar coordinates. If I'm talking about rectangular coordinates, I've only got one set. The only way in rectangular form to get this vector is to graph this x plus yi. This 5 minus 4i is the only rectangular form that's going to get me this specific vector. But in polar form, I have an infinite number of options. When I'm in polar form, there's literally an infinite set of possibilities because I can just keep rotating. In fact, we started with 1. If I hadn't specified that I wanted the least positive angle value for theta, I could have said square root 41 CIS negative 38.6598 degrees. That's the same location. That is right there. I could have rotated a full 360 clockwise, which would have been subtracting 360 from this, and I could keep going. Or I could keep adding 360 and keep going, and I would end up with an infinite set of polar coordinates. So that's just a little taste of what we're moving to for the next section.